ticket hypothesis, finding sparse, trainable neural networks. This work was presented by Frankle and Carbon at ICLR 2019. Why do we train large neural networks only to prune them later? The observation is this: networks can often be pruned by 90% or more without losing any accuracy. Neural network pruning process. The typical process for neural network pruning is train a dense network, prune low-magnitude weights. But why not train the small, sparse network directly? The lottery ticket hypothesis. The lottery ticket hypothesis proposes that a dense, randomly initialized network contains subnetworks that, when trained in isolation, can match the test accuracy of the original network. This subnetwork is called the winning ticket, a sparse subnetwork with a lucky initial weight configuration. Finding winning tickets. Iterative pruning algorithm. The winning ticket is found using the iterative pruning algorithm. Randomly initialize the network. Train for J iterations. Prune the smallest weights, for example, 20%. Key step: reset the remaining weights to their initial values. Repeat steps 2 through 4 until the target sparsity is reached. The most important takeaway here is that you reset the weights, not the architecture. Experimental results. When we look at the results, we plot the percent of weights remaining against the test accuracy. The winning ticket consistently learns faster and reaches higher accuracy than a network with a random reinitialization of the same sparse architecture. Why initialization matters. The combination of architecture and initialization is crucial. Original initialization, winning ticket. Random reinitialization trains efficiently, trains slowly, matches full accuracy. Lower accuracy, learns faster, struggles to learn. Key experimental findings. Winning tickets are found at only 10% to 20% of the original network size. The hypothesis works across various data sets like NIST and CIFAR-10 and multiple architectures. Winning tickets can train 3 to 5 times faster than the full dense network. They often achieve higher test accuracy, indicating better generalization. It requires a learning rate warm-up for deeper networks. Implications and future directions. The lottery ticket hypothesis has major implications for training efficiency. Find winning tickets early, which leads to faster training. Architecture design. Learn from the structures of winning tickets to design better networks from scratch. Theoretical understanding. Answering why winning tickets exist can lead to better optimization theory. The lottery ticket conjecture. The conjecture states that dense networks are easier to train because they contain more possible subnetworks, which increases the probability of finding a winning ticket. Iterative pruning in action. Example. Let's see the iterative pruning rounds. Round 0, full network, 100% remaining. Round 1, 80% remaining. Round 2, 60% remaining. Round 3, 40% remaining. Round 4, 20% remaining. This is the winning ticket. Winning ticket versus random sparse network. The performance due to the architecture or the initialization. Winning ticket, original init. Random sparse, random init. Accuracy, 98.5%. Accuracy, 94.2%. Training time, 10,000 iterations. Training time, 25,000 iterations. The answer is clear. Both the architecture and the initialization are crucial. Challenges with deeper networks. The challenge. Standard iterative pruning fails for deeper networks like VGG19 and ResNet 18 when using high learning rates. The solution: Implement a learning rate warm-up. This involves linearly increasing the learning rate from 0 up to the target rate over the first 10,000 to 20,000 iterations. This technique enables finding winning tickets even at high learning rates. Theoretical implications. The hypothesis raises fundamental questions. Why do winning tickets exist? What makes an initialization lucky? Why is over-parameterization so helpful? The current hypothesis is that lucky initializations land in regions of the loss landscape that are particularly amenable to optimization by